Okay, in chapter 4 we will discuss the exponential and logarithmic functions. Two important functions. They are used a lot in the applications. This is what we will cover in this chapter. Before we discuss the exponential functions, we need to study the concept of an inverse function. We have a definition. A function f is 1-to-1 if for a and b in the domain of f. If a does not equal b, then f of a does not equal f of b. That means if a and b are two different elements in the domain, then their images are two different elements in the codomain. The same condition can be written as f of a equal f of b means that a equals b. If the images are the same, then the pre-images are the same. For functions defined as ordered pairs, what you want to do is look at the ordered pairs. You cannot have two ordered pairs that have the same second element but different first element, because that means you have two different elements in the domain mapped to the same element in the codomain. This example here, f is 1-to-1. F has 1, 3, 2, 4, and 6 and minus 2 is an example of a 1-to-1 function. For g is not 1-to-1. It is a function. It is not 1-to-1 because 1, 3, and 6, 3, they have the same second element, the same y, but different x's. This function is not 1-to-1. You can tell if a function is 1-to-1 or not from the graph using the horizontal line test. For example, if a function is not 1-to-1, then you can find a horizontal line that crosses the graph of the function in two different points. What that means, you have two different values for x sharing the same value for y. If a function is 1-to-1, then every horizontal line will cross the graph in at most one point. Certainly then if you have a graph for the function, it should be easy enough to tell whether the function is 1-to-1 or not. A function g is the inverse of f if the composition of f and g is equal to x for all x in the domain of g, and the composition of g and f is also equal to x for all x in the domain of f. You can think of the inverse function that it reverses the action of f. Whatever f does, g does the opposite. The inverse for the function f is denoted by f. This is not a power. It looks like f to the power minus 1, but this is read the inverse of f. The way to find the inverse function, if f is 1-to-1, you'll be able to find the inverse. The first step is to replace f of x by y, then interchange x and y, solve for y, and the last step, replace y by f inverse of x. As far as the graph is concerned, the graph of a function and its inverse are symmetric with respect to the line y equal x. You could think of the graph of f inverse as a reflection of the graph of f about the line y equal x. Here is an example to find the inverse function. F of x equal 3x minus 2. We want to find the inverse. The first step is replace f of x by y. So you have y equal 3x minus 2. Interchange x and y. For x equal 3y minus 2. Now solve for y. Y is equal to x plus 2 divided by 3. Replace y by f inverse of x. F inverse of x is equal to x plus 2 divided by 3. Now you can check that the composition of the two functions both ways will give you x. For example, f of inverse of x. طبعا start with f, replace x by f inverse. f of x is equal to 3x minus 2. Replace x now by x plus 2 divided by 3. طبعا if you simplify, you will get x plus 2 minus 2, which you get x. The other way to compose f inverse, then you evaluate f inverse of f of x. So start with f inverse, replace x by f of x. Where you have 3x minus 2 plus 2 divided by 3. This is 3x over 3, which is equal to x. Where the composition both ways will give you x. Here is the graph for the two functions. F of x equal 3x minus 2 is the straight line in blue. The reflection of this line about the line y equal x will give you f inverse, which is defined as x plus 2 divided by 3. Now we can define the exponential functions and also define the logarithmic function. Let b be a real number, b is greater than 0, and b is different than 1. Then for any real number x, a function of the form f of x equal b raised to the power x is an exponential function. b here is called the base. طبعا the base has to be positive, and we don't use 1 for a base because you end up with a constant function. But here the base is positive and different than 1. The variable now is the power. This is called the exponential function. Now, as we will see, the graph of the function depends on the base, the value for b. If b is positive, f will be an increasing function. If b is between 0 and 1, then it will be a decreasing function. The domain f of x is defined for all x, all real numbers. The domain is from minus infinity to infinity. The range, you only get positive values. Anytime you take a positive number or raise it to any power, the result will give you a positive number. For the range is between 0 and infinity. The line y equals 0 will give us a horizontal asymptote, which means that the function will get closer and closer to 0. In the case where b is greater than 1, and you have an increasing function, the function will approach 0 if the power approaches minus infinity. In the case where the function is decreasing, when b is less than 1 and greater than 0, then the value of the function will get closer and closer to 0 as x approaches infinity. But in both cases, the horizontal, the x-axis will work as a horizontal asymptote. The function passes through 0, 1. This is regardless of the value for the base. When x is equal to 0, anything raised to the power 0 will equal to 1. For all exponential functions will pass through this point, 0 and 1. Here is the two different exponential functions with different bases. f of x equal 2 to the x. This is an exponential function with base equal to 2, where the function will be increasing. This is the graph in blue. The base is 2, where you'll see that it is an increasing function. It passes through the point 1, 0. This is actually a mistake. Actually, this point is 0, 1. 0 for x and 1 for y. Here is what we mean by the x-axis being an asymptote. As x approaches minus infinity, the function gets closer and closer to 0. The second function, which is in red, g of x is equal to 1/2 raised to the power x. B here is less than 1, greater than 0, where the function will be decreasing. But as the function increases, the value for y gets closer and closer to 0. This is a printing error. This should be actually the point 0 and 1. We have a special base that we use with the exponential function, starting with an irrational number we call e. This is just the limiting value of the expression 1 plus 1 over x raised to the power x. Yani this number gets closer and closer to a fixed value. That value is called e. Yani this is the value of the limit of the expression 1 plus 1 over x raised to the power x as x approaches infinity. طبعا this is an irrational number. It's a well-known number in mathematics. It is approximately equal to 2.171828. طبعا this is a number rounded to 6 decimal places, but since it's an irrational number, يعني the representation just continue indefinitely. But approximately, yani the value for e is can be rounded to a any number, any desired number of accuracy. Now, transformation can be used to graph an exponential function. Yani we can use e as a base. طبعا e is larger than 1, but that will be an increasing function. طبعا يعني you can have a function that يعني part of the function is the exponential function. For example, f of x equal e to the x minus 3. You can start طبعا with y equal e to the x, which is in the graph. This is a function in brown. طبعا it does go through the point 0, 1. It's an increasing function. If you want to graph e to the x minus 3, here every y value is shifted down by 3 units. The shape of the graph is the same, but for e to the x minus 3 you get this graph. طبعا every point of the original graph gets shifted, يعني the value for y, you subtract 3 from each value, but the result will be the graph which you see in blue here, f of x equal e to the x minus 3. There are some applications we can look at the problems involving interest. طبعا you have simple interest. This is not an exponential formula. Interest equal the principal times the rate times the time that you leave the investment. For I equal P times R times T. This is simple interest. The other way to calculate interest, this is called future value A with interest compounded n times per year. طبعا future value, that means the amount you started with plus interest, يعني the balance after length of time t. Then this formula P, طبعا A is the future value, principal plus interest. P is the original amount you started with times 1 plus R over N. R is the rate, and N is the number of times we compound the interest. All this is raised to N times T. طبعا T here is the time. But the variables here is طبعا A and T. The other way to calculate interest is A equal P times e to the RT. Here this is a future value A with interest compounded continuously. Any of these formulas can be used to calculate the interest. Here are examples of calculating interest. Suppose that $8,000 is invested at 5.4% interest. Compute the amount in the account, the future value, at the end of 3 years under the following compounding options. These are different options, but in all of them the principal will be 8,000. the rate is 5.4, and the time is 3 years. Quarterly, that means you compound 4 times a year, n is equal to 4. فهير طبعا in this formula P is the principal, which is 8,000. R is the rate. 5.4% is just 0.054 divided by 4 because n is equal to 4, raised to the power n times t, which is 4 times 3. The time t is 3 years. طبعا if you plug this in your calculator, you should get $9,396.69. This is a future value. طبعا this includes the principal plus the interest. If you want to calculate just the interest, then take A and subtract 8,000. That will give you how much interest was gained in 3 years. Continuously, the formula for that, the future value A is P times E to the RT. This is 8,000 times E raised to the power 0.054 times 3. طبعا you need a calculator for that. All scientific calculators will have the function E, the exponential function. You can plug this in your calculator. You should get $9,406.88. Now we're ready to define logarithmic functions. Logarithmic functions are basically the inverse functions of exponential functions, as we will see. If x and b are positive real numbers and b does not equal 1, because we exclude that from the exponential function, for the function now y equal log x to the base b, and this is how we write it, y equal log, the variable here is x, to the base b, where b is positive number other than 1. This is called the logarithmic function with base equal to b. What that means, this is just the inverse function of the exponential function with base equal to b. For y equal the log of x to the base b, if and only if b to the y is equal to x, or x is equal to b raised to the power y. You can think of these now, y equal log x to the base b is the logarithmic form, and b to the y equal x is the exponential form. Those two functions are inverses of each other. For example, this is the log function. This is defined for any base b greater than 1 and b does not equal 1. Now there are special bases, like if the base is 10, yani y equal log x to the base 10 is just written as the log of x. The base is not written. Any other base, with the exception of e, you have to write the base. Anyway, for the base 10, the base is not written, you just write log x, and this is called the common logarithmic function. For the other special base, if it's the number e, then log x to the base e is written as ln, this is read ln, ln is ln x. This is just the natural logarithm. So this is just the log to the base e. We will look at examples of using the log function to different bases. For example, if you look at the log function to the base 2, log x to the base 2, the exponential form here, now that x is equal to 2 to the y, or 2 to the y equal x. Now in this function, y is called the logarithm, 2 is the base, and x is the argument. This is a number that you apply the log to. Here are some examples of applying the log function. Log 16 to the base 2 is equal to 4, because 2 to the 4 equals 16. You can think of the log of a number to a certain base is the exponent that you raise the base to get the number. The log 16 to the base 2 is equal to 4, because 2 to the 4 equals 16. log 100 is equal to 2. طبعا log is the base 10. Log 100 to the base 10 is equal to 2 because 10 to the 2 is equal to 100. The third example, log 1 over e is equal to minus 1 because with the ln the base is e, e raised to the power minus 1 is equal to 1 over e. The log يعني sometimes it's easier to think of it that the log of a number to a base is the power that I raise the base to get the number. Here are يعني basic properties of logarithm. Log 1 to any base is equal to 0 لأن b to the power 0 is equal to 1. Log b to the base b is 1 لأن b to the 1 equal b. Now log b to the x to the base b is equal to x لأن these are inverse functions of each other. And if you apply the exponential function first, b to the x, and then apply the log to the same base, you always end up with x. These are inverse functions of each other. Number 4 also follows from the fact that the two functions are inverses. And if you apply the log function first and then the exponential function, yani b raised to the power log x to the power b will also give you x. Just yani 3 and 4 follows from the fact that the exponential and the logarithmic function to the same base are inverses of each other. Here is another example. Log 1 to the base 5 is equal to 0 because 5 to the 0 equal 1. Log 7 to the base 7 is 1, then 7 raised to the power 1 is equal to 7. Ln, this is just log to the base e, for ln e to the 5 is equal to 5. And e raised to the power 5 gives you e to the 5. The last one, this is the log طبعا is the base 10. For 10 raised to the power log x plus 5 will give you x plus 5. And these are يعني the log to the base 10 and the exponential to the base 10 are inverses of each other. Let's look at the graph of the logarithmic function f of x equal log x to the base b. The log, as you would expect, طبعا the graph will depend on the value for b. If b is greater than 1, the function will be an increasing function. As you can see in the graph, the blue graph represents f of x equal log x to the base 2. Since the base is equal to 2, which is larger than 1, the function will be increasing. But if you think about it, this is the inverse function for the exponential function 2 to the x. If you think of the reflection of an increasing function, it will be also an increasing function. The second case, if the base is greater than 0 but less than 1, the function will be decreasing. As you can see, the red graph here is a graph for f of x equal log x to the base 1/2. 1/2 is less than 1, where the function is decreasing. Both functions have to pass through the point 1, 0, لأن the log of 1 is equal to 0. Another way to look at this, since the log function is the reflection of the exponential function goes through the point 0, 1, wherein the log function will go through the point 1, 0. There is more information that you can get from the graph. You notice that the log function is defined only for positive real numbers. It is not defined for 0. It is not defined for negative numbers. طبعا we know as x approaches 0, يعني if you get closer to 0, the function either will go to positive infinity or it will go to negative infinity. That's what we mean that the line x equals 0 or the y-axis work as a vertical asymptote. There are actually many things that we can get from the graph, but the main thing here now, the argument of, when you say the argument to a logarithmic function must be positive, لأن the log is not defined for negative numbers. Here is that fact stated again. The argument to a logarithmic function must be a positive real number. And you can use this to determine the domain for a function that involves the logarithms, such as in example 5 we have f of x equal ln 3 minus x. طبعا you can think of this as a composite function, but the argument here is 3 minus x. That cannot be negative. فإذا to find the domain for f, 3 minus x must be greater than 0. طبعا you solve this, you will get that x is less than 3. But the domain for f would be x less than 3, or it is the open interval from minus infinity to 3. Section 4.4, we will look at some properties of logarithms that will be useful to solve equations. Here in those properties, b, x, and y are positive real numbers, with b does not equal 1, then b will be the base. For the first rule, that the log of the product, yani log x times y to the base b, is equal to log x to the base b plus log y to the base b. The product property, you can remember it by saying the log of the product is equal to the sum of the logs. For division, you subtract. For log x over y is equal to log x minus log y. طبعا all those terms have the same base. This is called the quotient property. The third property deals with the power. For log x to the power p is equal to p times log x. Yani you're applying the log to a power of x, you can just multiply the log by this power. This is called the power property. Now these rules can be used yani both from left to right and from right to left. Just like the first rule, the log of the product is the sum of the logs. If you have an expression where you have the sum of the logs to the same base, you can write it as a single log. You can write it as log x times y. Same thing for the second formula. If you have the difference of two logs for the same base, you can write it as the log of the quotient x over y. Here you have an expression that have more than one log. Using this property, you can write it as one log. In the first case, it is log of the product. Yani the sum of logs can be written as the log of the product. The difference of two logs can be written as the log of the quotient. Same thing for the third property. If you have p times log x, you can write it as log x to the power p. A single logarithm expression can be written as the sum or difference of logarithms. Here are some examples to apply those rules. Log 9y, this is base 3. طبعا log of the product is the sum of the logs. So this is log 9 plus log y. Log 9 to the base 3 is just 2. Then 3 squared is equal to 9. And there is you can't do anything with log y, but just leave it like it is. Log 100 over t is log 100 minus log t. طبعا log 100 is 2. Then 10 to the 2 is equal to 100 minus log t. Log the cube root of w is just log w raised to the power 1 over 3, which is equal to 1/3 times ln w. You can just take the power and write it, multiply the ln by the power, which is in this case 1 over 3. Now, applying the log to an expression will simplify it by using those rules. For example, log, if you apply the log function to this expression, 5x to the power 7 divided by the square root of y, start by applying the quotient rule. This is log 5x to the power 7 minus log the square root of y. Then apply the product property. This is log 5 plus log x to the 7 minus log y to the power 1/2. Now apply the power property. This can be written as log 5 plus 7 log x minus 1/2 log y. We will see in this property sometimes is used to solve equations. Those properties are quite useful, as we will see, and we will use the log to solve equations. The sum or difference of logs can be written as a single logarithm. Using the same rules, as we see that the log of the product is equal to the sum of the logs, using the same formula, then the sum of the logs can be written as one log, as the log of the product. But these formulas can be used both directions. We will see how to apply this. For example, the expression ln c plus ln a squared minus b squared minus ln a plus b. Now the sum of the first two terms, ln c plus ln a squared minus b squared, can be written as one logarithm as ln the product of c and a squared minus b squared minus ln a plus b. The difference of the two terms, these are the difference of two logarithms. It can be written as the logarithm of the quotient. For this is ln c times a squared minus b squared divided by a plus b. You can simplify the expression inside the bracket a little more. But this can be written as c times a plus b times a minus b. Now you have a common factor, a plus b. You can cancel that, and you end up with ln c times a minus b. The other thing that we need to know is the change of base formula, which is actually a useful formula if you want to evaluate. Most scientific calculators will have ln, will have the log to the base e, and will have log functions, which is the log to the base 10. But if you want to apply, do calculations involving the log of bases other than e and 10, you could use the change of base formula to evaluate the logs, and using the calculator. For here, you have positive real numbers a and b, and as usual, a and b do not equal 1, and these will work as bases. For log x to the base b can be written as log x to the base a divided by log b to the base a. Remember, now you started with a log to the base b, and you are writing it in terms of another base. Log x to the base b is equal to log x, log of the argument, this time to the base a, divided by the log of the original base to the base a. We will see that. In this case, then, if you want to evaluate a log to a different base other than 10 or e, just change the base to base 10 or base e, and you can use your calculator to evaluate the log. For the change of base formula is often used with base 10. You can also use base e. This way you can use your calculator to evaluate logarithms to a base different than 10 and e. Here is an example. Use your calculator to approximate log 806 to the base 2. Now we want to change the base to, let's use base 10. For log 806 to the base 2 is equal to log 806 to the base 10, log 806 divided by the log of the base, log 2. Log 806 can be evaluated using a scientific calculator. Divide that by the log of 2. You should get approximately, this is rounded now, approximately 9.6546. This is rounded to 4 decimal places. Let's do the same problem but using the base the ln يعني base e. log 806 to the base 2 is equal to ln 806 divided by ln 2. It will be 9.6546, and at least to 4 decimal places you get the same answer. طبعا يعني if you want to check, this is, remember this is an approximation. For example, working يعني you evaluated now log 806 in both ways to the base 2 to equal to approximately 9.646. That means if I raise 2 to this power, I should get a number, the number 806 or something very close to it. If 2 raised to the power 9.6546 is equal to 806. Also now we would like to see how we can handle exponential and logarithmic equations, how to solve them. We have a property that will be useful. This is called equivalence property for exponential expressions. Here b, x, y are real numbers, b greater than 0 and b does not equal 1. If b to the x equal to b to the y, then x is equal to y. Yani this is now the same base, raised, 1 is raised to the power x and 1 is raised to the power y. If those two quantities are equal, then the powers must be equal. If the base is the same, then the powers are the same. And this is actually, yani, you can use this to solve equations involving exponential terms, as we will see in example 1. Here we want to solve 27 raised to the power minus 2x plus 1 equals 1 over 9 raised to the power x. طبعا the trick is to write the left hand side يعني, and the right hand side as a power of some number and using the same base. 27 is just 3 cube, and you have a 9 يعني in the right hand side, which is just 3 squared, so clearly the common base will be 3. If I start by writing 27 as 3 to the power 3 raised to the power minus 2x plus 1, the left hand side is just 1 divided by 3 squared, or 3 to the power minus 2. Now on the left hand side multiply the outside and inside power, so you get 3 raised to the power minus 6x plus 3. The right hand side becomes 3 to the power minus 2 times x. And now you have written them both as a power of the same base. Since the two sides are equal and both of them are powers of the same base, then the powers must be equal. Okay, then minus 6x plus 3, which is the power on the left hand side, is equal to minus 2x, which is the power on the right hand side. Now you have a linear term which is easy to solve. Just add 2x to both sides and subtract 3. You get minus 4x is equal to minus 3. Divide by minus 4. Your solution will be 3 over 4. That's the solution to the original equation. Also, we have a similar property for logarithmic expression. This is called equivalence property of logarithmic expression. As usual, b, x, and y are positive and b does not equal 1. If log x to the base b equal to log y to the base b, then x is equal to y. By the way, this is true. طبعا you can think about it. يعني the same way for the exponential function. These are one-to-one functions. The log and the exponential functions are one-to-one functions. If the images are the same, then the arguments are the same. If log x to the base b is equal to log y to the base b, then x must equal to y. This follows from the fact that the log function is one-to-one. The same thing for the exponential function. Let's see how we can use this to solve equations. Solve the equation log 5x minus 1 equal log 4x plus 6. طبعا here the base is 10. Since the two sides are equal, log to the same base, and then the arguments must be the same. And 5x minus 1 equals 4x plus 6. And again, you have a linear term that should be easy to solve. Subtract 4x from both sides and add 1. You get x is equal to 7. You can actually check by substituting x equals 7. Log 5 times 7 minus 1. Does that equal log 4 times 7 plus 6? So the left hand side is just log 34, and the right hand side is also log 34. 7 will give you a solution for the original equation. Next, we would like to see how to solve exponential equations, this time by applying log. Since the exponential is the inverse function of the log, anytime you see an equation that have an exponential form, you can try to solve it by applying the log to both sides, طبعا to the same base. Here is an example. You have 5 to the x equal 413. Apply now. You can actually apply the len or the log. Apply len to both sides. Okay, then the left hand side, len 5 to the x is equal to len 413. You can write this now as x times len 5 equal len 413. X is equal to len 413 divided by len 5. This, you use a calculator, you will get approximately, the result is 3.7426. This is rounded to 4 decimal places. Next, we would like to see how we can solve logarithmic equations. These are the general guidelines, and we will apply them to see how we can solve a logarithmic equation. The first step is to isolate logarithms on one side and طبعا everything else to the other side. Number 2, we want to use the properties of logarithms to write the equation in the form log x to the base b equal k, where k is a constant. Now if you write this equation in the exponential form, you will have x equal b to the k, and that will give you your solution. طبعا the solution involves the definition of the logarithmic functions. Check for the potential solutions in the original equation. After you solve the equation in step 3, make sure طبعا your solutions will check. They will be in the domain of the logarithmic function. In the next slide, we will solve an example. This will show us that طبعا after you write the solutions, make sure that the solution in the last step will be in the domain of the logarithmic function. In the next slide, we will end up with 2 solutions, 2 and 6, but it turns out that 2 will not be in the domain. We will have a term log x minus 5 to the base 3. If we do perform all those steps, we will end up with 2 solutions, 2 and 6. You can use the 6, it will be one of your solutions, but the 2 will not work because it's not in the domain. You have to be careful that your solutions are in the domain of the logarithmic function. And that's طبعا we haven't done the example. This is just the idea is that you have to be careful, is that your solution must be in the domain of the log. This is what we will do now. We want to solve log x minus 5 to the base 3 equal 1 minus log x minus 3 to the base 3. The first step is to isolate the log terms on one side. If I take minus log x minus 3 to the base 3, take it to the other side. So you have log x minus 5 plus log x minus 3. Both are logs to the base 3. This is equal to 1. Now use the properties, the sum of the logs is equal to the log of the products, where the left hand side becomes log x minus 5 times x minus 3 to the base 3. If you multiply, you will get log x squared minus 8x plus 15 to the base 3 is equal to 1. Now what that means is that the argument x squared minus 8x plus 15 is equal to 3 to the 1. That's from the definition of the log, which is equal to 3. Now subtract 3 from both sides. You get x squared minus 8x plus 12 equals 0. You can factor this term as x minus 6 times x minus 2 equals 0. But you have two solutions, x equals 6 or x is equal to 2. Now this is the comment we said earlier, is that even though 6 and 2 are both solutions to this equation, but 2 is not in the domain of the log. And if you substitute 2 in the original expression, you will get log minus 3, and the log of a negative number is not defined. But yes, it is a solution for the final equation, but it just happens to be not a number in the domain. But we do not take 2 as a solution. But you only have one solution, which is x equals 6. The final section, we want to do some modeling using the exponential and logarithmic function. The function defined by y equal y0 e to the kt represent, we call it exponential growth, with k, if k is greater than 0 طبعا, this is now a positive number times t, so it will be an increasing function. That's why we call it exponential growth. If the power k in the power is negative, then actually this will be a decreasing function. As t increases, this is a negative power, the function will decrease. In this case we call it exponential decay. And we will find in both cases this can be used as a model for some situations. An exponential expression can be rewritten as an expression of a different base. In particular, we saw this before. To convert to base e, we have b to the t is equivalent to e to the ln b times t. Remember now this term here, e to the ln b times t, is the same as e to the power ln b, and everything is raised to the power t. The exponential is the inverse of the ln, so you end up with b raised to the power t. But certainly this expression b to the t can be rewritten as e to the power ln b times t. So you can always work with an exponential form where the base is equal to e. So here is the exponential models are used a lot for populations. Population tends to grow. An exponential growth is often used to describe a population. In this example, the population of Virginia, this is one of the United States, the population of Virginia was 7.1 million in the year 2000 and grew to 8 million by the year 2010. Write a model of the form P of t equal P0 times e to the kt. P0 represents the initial population. If you look at this model, P of 0, the power, when you substitute t equals 0, you have e raised to the power 0, which is 1. So you're left with P0. Then P0 is called the initial population. This is the population at the beginning of time, at the beginning of your model. P0 represents the initial population. T is the variable that represents time in years, and k is the constant that will give you the growth constant that will give you the model. The object here is always with things like that is P0 is normally given. the initial population is given. It's a matter of finding k. Yani use the information to find k. We've done this before. Yani once you find k, the constant, then you can substitute it in the model, and that will give you an equation which is will give you your population model. Okay, this is what we are looking for now. P of t equal P0 e to the kt. P0 is just 7.1 million. You have 7.1 e to the power kt. Now to find k, remember when t is equal to 10, and after 10 years, the population is 8 million. Substitute t equal 10, and for the population p of t, substitute 8. And now it's solving an exponential function. You can do this first by dividing both sides by 7.1. You have 8 divided by 7.1 is e to the 10k. Apply the ln. Then ln 8 over 7.1 is equal to 10k. And now k will equal to ln 8 over 7.1 divided by 10. You need a calculator for this. You will get k to equal approximately 0.0119. This is a constant rounded to 4 decimal places. Now that you know k, you can substitute it back in the model, where your population p of t is equal to 7.1 times e raised to the power 0.0119 times t. By the way, since you have the model, now you can find the population at any given year by substituting the value for t. You can also use this type of equations. For example, if you want to know when will the population equal to a certain number, you can substitute that number for p of t and solve for t. But there's all kind of things. Once you determine the model for the population, the model is just an equation. You can use it to answer many questions. Here is an example that we have a model with base equal to 0.5. We would like to rewrite it so that the base will be e. So we have y equal 400 times 0.5 raised to the power 0.03 t. The first step is we can write the expression as 400 times 0.5 raised to the power t, and everything raised to the power 0.03. Now if you multiply the outside and inside power, you'll get the model you started with. So we have not changed anything. Now in the next step, this 0.5 can be, you can apply the ln and the exponential, so you have not changed the number. You can write it as e to the ln 0.5, and it is raised to the power t. It can be written as e to the ln 0.5 times t, and outside you have the power 0.03. Now bring 0.03 inside and take t outside. Again, when you multiply the outside and inside powers, you end up with the same expression. So you have e to the ln 0.5 times 0.03, and the t now is outside. And every time, when you think about it, when you multiply the outside and inside power, you get the expression that you had in the previous step. Now why do we do all this? Now ln 5 can be evaluated using the calculator and multiply it by 0.03. Now you will have, the ln 0.5 will end up being a negative number, so this power here becomes minus 0.0208 times t. The t is the power from outside. All this work is, what you have now is a model, but now the base is e. Instead of having the base 0.5, you have a base which is equal to e. The final model that we like to look at is another growth model, but it is growth to a limit. This is called logistic growth function. It's an exponential growth, but to a limit. That means y is bounded by a fixed value, and we will see the picture will explain why this is a logistic growth function. It has this form: y equal c divided by 1 plus a times e to the minus bt. Notice that in the denominator, this expression here, e to the minus bt, this has a negative power. As t increases, this quantity will decrease. This is always bound by c, and this value here is always less than c. Even when t approaches infinity, the value will approach c. And as t approaches infinity, this part of the expression approaches 0, and the limit will be c. The value of y is always under the line y equals c. This is called the logistic growth function. It imposes a limiting value on the dependent variable. Here is a picture. In fact, there is an example here. Y is equal to 42.6 divided by 1 plus 9 times e to the minus 0.35t. This is logistic growth. You can see that the functions start increasing quickly, but then you reach a point where the growth slows down. The y value is always under the line y equal 42.6. There is a limiting process. It is a growth, but bound by a value. It is there is an upper limit to the value for y.